So the synapse, right? We talked about this before, right? Where the neuron is going to synapse with, in this case, a muscle. But this synapse could be another neuron, right? If it's specifically a synapse that connects a nerve with a muscle, then we call the synapse a neuromuscular junction. Okay? So all neuromuscular junctions are synapses, but not all synapses are neuromuscular junctions. Okay? And that's what I just reiterated here. Okay? And keep in mind that at the end of it, when it comes to the synapse of a neuromuscular junction, acetylcholine is the neurotransmitter that's going to get released. So here's a new term for you. Any neuron that releases acetylcholine is known as a cholinergic neuron. You're going to see that quite often. Okay? When we get into the autonomic nervous system, you'll see it a lot there too. All right? So we just refer to it as a cholinergic neuron. Any neuron that releases or secretes acetylcholine as its neurotransmitter in its synapse. Okay? So just to reiterate, right? Action potential comes down here. Here's the axon terminal. It's going to, once the action potential reaches the axon terminal, it's going to open up channel gates over here. Calcium gates over here to allow calcium that's sitting around in the synaptic cleft to go into the cell, specifically into the axon terminal. That calcium will bind to the vesicles that are at the axon terminal and contain the green dots here as a neurotransmitter, in this case it being acetylcholine. Once calcium binds to the vesicles will then fuse with the presynaptic membrane, and through exocytosis will release the neurotransmitter across the cleft, okay, until it reaches the receptors on the postsynaptic, what is that, mine? Yeah. Sorry. So once acetylcholine gets released across the synaptic cleft, across the Delaware River, it reaches its receptors on the postsynaptic membrane. Okay? And that's going to set off an action potential in the muscle here, if this is the muscle. Okay? I remember this. Okay. All right? Then we have the acetylcholine. If the green dots are acetylcholine, those are the ones that are going to stay there. And it's kind of like, I don't want to say pushing a button, but it goes through the receptor and allows the sodium to come in, makes inside more positive, but then you're also going to have some potassium going out. This is going to spark up an action potential on this side. This is a muscle, then the action potential is going to spread over the sarcolemma, go into the T tubules. You know the whole story about myosin and actin contracting over there. Okay? If this is a dendrite of another neuron, then it's going to start an action potential to go into the cell body of this neuron. Okay? But as long as this neurotransmitter is on here, you're going to still continue to stimulate this cell. So we have, if this is acetylcholine, we have something out that's over here called acetylcholine esterase, okay, which is an enzyme that will break up this acetylcholine to allow it to come off of this, and then you won't have that cell being stimulated. Okay? Is that a good review of this? Okay? So, in summary, just so you hear it again, the action potential goes, if I'm spending that much time on this, there's going to be questions on the test, right? So an action potential goes through the nerve axon, all right? Sodium goes in, potassium goes out, until it reaches its axon terminal end. That's going to depolarize that end, allow calcium to come into the axon terminal, and the calcium is going to bind to the vesicles that contain the neurotransmitter, in this case acetylcholine. The vesicles will then fuse with the presynaptic membrane, and through exocytosis, acetylcholine gets released into the synaptic cleft. The acetylcholine binds the synaptic the binds to the receptors on the postsynaptic membrane. Okay, and this is where local potential is being created. Okay, if acetylcholine is going to stay there for a long time, you're going to have more sodium go in, thus it's going to create an action potential once it reaches negative 55. If you only have a little bit of acetylcholine going there, it may go up from negative 70 to negative 60, but never reach threshold. The muscle action potential, if it does occur, reaches negative 55, then it's going to spread across the muscle, the sarcolemma, the muscle membrane, cell membrane, go down the T tubules, and the action potential comes in close contact with the sarcoplasmic reticulum when we're dealing with those triads. And it's going to tell the sarcoplasmic reticulum somehow, we don't know the actual mechanism, but somehow it's going to tell the sarcoplasmic reticulum to release the calcium that's stored inside the sarcoplasmic reticulum. Now you're going to have calcium floating all over the sarcomeres. And that's going to, the calcium will actually bind to the troponin to change shape on the actin so that we can expose the myosin binding sites. So myosin binds to that and causes a contraction. In the meantime, what's going to stop that from contracting, we got to stop the action potential. So we have acetylcholine esterase in the Delaware River upstream from where the muscle is, and it's going to start breaking up some of that acetylcholine to come off those receptors to stop pushing that button. Okay? And it's doing that. If these steps here, 1 through 7, are steps over here, 1 through 7. Okay? You can see it over here also. It's always good. That's how I learned in college and medical school. If you understand it in one picture, don't end it there. Look at a different picture, another diagram, another book, another, now you have the internet, so look at different pictures on there. If you understand it here, to reinforce it for yourself, look at 5 other different ways. It should all be the same. But now you're looking at it going this way, or the way they word it up here. You'll get used to different ways of saying the same thing. That's what's going to train you to deal with my exam or anybody else's exam because of the way they're saying it. Whether it's going to get released, secreted, exocytosis, it's all the same thing, but you got to know these terms. Okay? So again, this is where acetylcholine binds over onto these channels. When it does, it unlocks the doors and allows the sodium to come into the cell. Okay? Just showing you again what's happening there. Okay? And we talked about all the different diseases and how it affects the neuromuscular junction. We talked about the black widow spider, botulism, Chiari, pesticides. It's not here to try and make this into a medical school. It's here to show you why this stuff is significant for you to know. Instead of just knowing the parts and call it a day, chances are most students will forget this stuff. But if you put black widow spider in there, you put botulism in there, studies have shown that students will actually remember this stuff for a longer amount of time because it has some meaning to it. Okay? All right, so let's talk about transmission types. Okay? Scary words, but they're easy to manage. Excitatory postsynaptic potentials, or ESPS, or EPSPs. Okay? Basically what this is that anything that's going to be stimulating the cell to go towards a threshold. Okay? We call that an EPSP. Okay? Anything that's going to get closer to threshold is going to be an EPSP. So if I asked you a medication that is going to open sodium channels Is that an EPSP? Is that going to get the charge inside closer to threshold if we open sodium channels? Think about it. Open sodium channels. Does sodium want to go into the cell or out of the cell? Into the cell. Does that make the cell more positive or more negative? Positive. Is that going to get closer to from negative 70 to negative 55? Are we going to be adding positive charge or are we going to be adding negative charge? Positive. So does it get it closer to threshold if we open up sodium channels? Yes. Okay? Does that make sense? Okay? So anything going towards positive, we call it depolarization. Then we have something called inhibitory postsynaptic potentials, or IPSPs. Again, still looking at the area where the local potential is, the negative 70 and negative 55. But remember, it can go up and down. It's graded. It could go up and down. Once you reach negative 55, it's always up. An IPSP is anything that's going to pull that charge further from threshold. Okay? So it's going to go more negative or less positive. Same thing. Okay? So if we open up chloride channels, I know it's written up there, but I want you to understand it. If you open up chloride channels, does chloride want to go into the cell or out of the cell? Think of the sodium or the salty banana. If you open chloride channels, does chloride want to go into the cell or out of the cell? Into the cell. Does chloride carry a negative charge or a positive charge? Or for you chemistry peoples, is a chloride ion, is it an anion or a cation? Anion, okay. So if chloride is going into the cell, is that making the cell more negative or more positive? Negative. Is that going to bring it closer to threshold or away from it? Away. This is what we call hyperpolarization. Okay, and we have medications that will open up channels, close channels, and that's what it's all based on. Okay? So an EPSP goes up. An IPSP goes down. But you can have this where it's going to go up and down, up and down. Okay? I'll show you that too. Now, we have something called presynaptic modulation. Now we're going to get into, this is not hard to understand, but it is making you appreciate how complex the nervous system is. Presynaptic modulation. You know what I'm drawing, right? Presynaptic modulation. So we're going to have it so that when acetylcholine is going to come out of here, it's going to come out and it's going to go to its receptors on the other side. Right? Old news to you guys. Okay? Now, presynaptic modulation. Ooh. All that's saying is that there's going to be another neuron that's going to modulate that. If this is going to produce a lot or secrete a lot of acetylcholine, then there's going to be something over here another neuron, and we have another synaptic cleft here that is going to control this. This can also produce a certain type of neurotransmitters. Might not be acetylcholine. It could be something else. And that's going to get released and go to its receptors. And the amount that this is going to do, this neurotransmitter may stimulate this to produce more over here, or it may inhibit this to secrete less over here. It's modulating the presynaptic membrane. And yes, you could have another one that's going to synapse on here, and another one over there. Ay, ay, ay. I don't even know how they came up with this. People with no social lives. It could get complex. But that's what this is, a presynaptic modulating neuron. And it can control that one. Okay? We could have presynaptic inhibition. Something that's going to say, hey, look, I want you to release less of this out here, so this is going to tell that to inhibit that neurotransmitter. A good example of this is endorphins. Endorphins is a type of neurotransmitter that will get released over here to decrease the neurotransmitters that's over here. Endorphins. You guys have heard of endorphins. This is the neurotransmitter that gives you that natural high. The idea that you're running, and yet if someone, I'm not saying go ahead and do this, but if someone punches you, when you build up all this endorphin buildup, you don't feel as much. You just feel like a thud, when really if you weren't running, if you didn't have all that extra, I don't know, all that extra energy it just gave off, then you would probably feel it as pain. So endorphins actually can inhibit pain sensation. If this is not a muscle, this might be another neuron that leads up to the brain. So this can actually inhibit this so that that neurotransmitter doesn't get released enough, so it won't go up to the brain and you don't interpret pain. Does that make sense? Okay? Presynaptic facilitation is the opposite. Not inhibition, but stimulation. And a good example of that is glutamate, also called glutamic acid. And this is a neurotransmitter that's excitatory. It can enhance nitric oxide release, which will dilate blood vessels. And when you dilate blood vessels, it decreases the blood pressure. Doing the same thing, but it's going to stimulate this. Okay? Questions about that? All right? So we call this a modulating neuron. It's going to modulate that neuron, another neuron. Okay? Kind of like what I drew for you. This is going to release a lot, but if this is an inhibitory neuron, then when this releases its neurotransmitters, it's going to inhibit this and release less. All right? Can you understand this? That's what I said. A&P is not hard. It's just throwing this with all your bones, throwing this with the brain, throwing this with muscles. It's more about time management. But if you isolate each section, it really isn't hard. You just got to be able to go through it and understand it in such a short time. All right, so these are the neurotransmitters. There's about 60 of them. I'm only asking you to know about a dozen. They're not so bad. We've known a few of these, but we talked about them. We have acetylcholine, okay, and I put some abbreviations over here so you can see them. But we have acetylcholine, and this could be excitatory or inhibitory. Depends on the receptor. And we'll talk about some of these when we get into the autonomic nervous system. We also have epinephrine, norepinephrine, and substance P. Substance P is a neurotransmitter that gets released for pain. So if there's a lot of substance P, I would imagine P stands for pain, but I don't think it's that easy. All right, probably some Latin word or something. But it's a neurotransmitter that gets released for pain. So if we could have a modulating neuron to decrease the amount of substance P coming out, then that will decrease pain. There are some medications out there that will do that. Those are painkillers, okay? All of these will either be excitatory or inhibitory. Depends on the type of receptor, okay? Then we have these over here, and these are all excitatory. We have dopamine, which we'll talk about when we get into Parkinson's disease, and basal ganglion. So dopamine, serotonin, also known as 5-HT, histamine, glutamate or glutamic acid, aspartate or aspartic acid. So these are all excitatory things. These are things that are going to facilitate and make more neurotransmitters get released. And these are the three that are inhibitory. GABA is the big one you should know. All right, it stands for gamma it's GABA. Okay, no, GABA or gamma aminobutyric acid. Okay, but this is the most abundant inhibitory neurotransmitter we have in our body. Glycine is another one I already mentioned about endorphins. So those are the ones that you should know that I think in A&P1, A&P2, when you're nursing, wherever you're going to go, those are the more prominent ones that I think that they'll be mentioning. There's a bunch of other ones. Just take for granted it's a neurotransmitter. If you need to read about it, then you can read about it. But these are the ones that are more commonly discussed in future classes. Now here's some things where you could actually apply this stuff. Depression. We know what people have in depression, and I mean major depression, where you have a depression. I understand there's depression where you get a grade back and you feel depressed. I'm not talking about that kind of depression. Depression where it's going to affect the way you eat, the way you sleep. It's lasting longer than a year. Okay, that's major depression. There's a lot of other features to it, but it's that. It's not something like you just feel depressed because it looks like a horrible day outside and you just got a bad grade on the exam. That's life. No, that's not depression. I mean, in this sense. But depression is a decrease in norepinephrine and a decrease in serotonin. So, what do you think the goal is in treatment of depression? Yeah, you're going to increase these two. You've heard of Prozac, right? Prozac is something we call an SSRI, selective serotonin reuptake inhibitor. All right, what that is, I realize that. Let's say this is, these green dots are serotonin. Okay, that's the neurotransmitter. But we need to put more of it out there. So what it's going to do, it's selectively going to take serotonin, and normally the serotonin is going to go back in here, right? Sort of the way acetylcholine does, to actually get recycled, to go back into vesicles. So this is, look, think about what it is. Selective serotonin reuptake, but we are going to inhibit it, allowing more serotonin to stay in this area here. Something that we kind of talked a little bit in mechanism about with myasthenia gravis, right? We put more acetylcholine out there, hopefully it's going to knock off those autoantibodies. Remember the good old days when we did that, right? All right. Did we do that? Yeah, we did that. Okay. All right. When I'm teaching 3 different classes at the same time, I'm losing which one I did with each class. So that's what an SSRI is, okay? I'm not going to ask you about that. I'm just showing you that this stuff is going to come back. I'm sure most of you are going to be taking courses of pharmacology. You're going to need to know this stuff, okay? Schizophrenia, Parkinson's. Look at Parkinson's disease. It's a decrease in dopamine. So what do you think is going to be the goal to try and fix Parkinson's? Yeah, increase dopamine. And that's exactly what we'll do. However, The problem is that you could increase it higher and higher, and we have the blood-brain barrier. There's only a certain amount that can get inside. But if we put a lot in there and it does go inside, it comes to it's a small window, because now it might get too high. And if it goes too high, it can actually cause schizophrenia. You see? In schizophrenia, what do you think the goal is? To decrease dopamine. But if they start getting Parkinsonian effects and they start shaking, it went too low. Are you getting to see, I'm not just doing this for the health of me, I'm doing this for you guys so you can take on stuff that you're going to be dealing with later on. Instead of just memorizing these things and forgetting about it, I hope to God that you guys review it later on and not relearn it. Those are two different words, and I don't want you to relearn this stuff. All right? I find that my students struggle in nursing and stuff, but they come back and most of them tell me that we are not struggling like other students. Okay? I put a lot of this kind of disease and medication stuff not to make this into medical school, but to make it so that, again, just to give this stuff meaning, to show you you're going to need to know this later on. Okay? And show you that draw pictures. They work. Okay? Questions about this? Okay? Alright, summation of synapses. We could have spatial summation. Spatial summation is basically, we could have 5 or 6 modulating neurons on this one neuron. And each one is going to give one pulse or one neurotransmitter from each one of these onto here. The sum of all of them will actually modulate this neuron here. So it's spatially, it's a bunch of different neurons modulating this. I'll show you a picture of what I mean by that. When they're added together, that's going to actually make that neuron release the acetylcholine and which not. Then we also have temporal summation. There's only one synapse. But what this one neuron is going to do is frequency. It's going to pound this one over here with more and more pulsatiles, more and more stimulation to cause that depolarization. So the frequency, the spatial one, a lot of different neurons are going to attack that, not attack it, but they're going to synapse with that one neuron, and it doesn't need that much from, they don't need the frequency. But if you only have one, then you're going to need to increase the frequency of that one. So what you got here is they're just showing 2 over here, but spatial, you're going to have one coming this way and one coming this way to tell that what to do. Does that make sense? Whereas temporal, there's only going to be one, but the frequency is very fast, enough that it's going to cause the action potential to go down this axon. Does that make sense between that? Yeah? Everything okay? You were going good. Yeah? Okay. There was a bug or something. Okay. And this is what I was trying to show you with a local potential. See, it can go up and down, up and down, up and down. Once it reaches negative 55, it's going to fire an action potential. Okay? So when you have this, spatial versus temporal, this is going to be temporal. So in one that's doing that. Alright? That's how crazy it looks. Each one of these purple things, they cut them off, but this is actually an axon terminal from another neuron. It gets busy. Okay? So I don't expect you to know each one of these things, but I want you to appreciate how complex the nervous system can be. Okay? Alright, neural circuits. Alright, pretty easy to do. Last thing I'll do with this part. Neural circuits is we have these synaptic stations. And we have axons that are going to go to certain neurons and do certain things with them. Okay? So we could have an axon go into a dendrite, an axon go into a cell body or soma, or an axon that can go to another axon. What I showed you here was an axon go into an axon. And what you saw over here is an axon going to a cell body. You see what I'm saying? All right. So here's the picture, kind of schematic. But we could have a neuron go into a dendrite, so an axon go into a dendrite, axon go into a cell body, or an axon go into an axon. So we have axodendritic, axosomatic, or axoaxionic. Now let's say that 5 times fast. Okay. Now, when we put it all together, we can have a lot of different things going on. So they're pretty self-explanatory when you look it over here, but I'll just write it over here. Negative feedback, what's going to happen is that this is going to send a message backwards to a cell, to the cell body, and say, whoa, you got too much of it. It's negative feedback. It's going to slow it down. Okay? We could also have lateral inhibition, meaning that we can actually have one cell that's going to synapse with another neuron over here. They can converge, or I'm sorry, diverge, but some of them can actually give you negative, meaning they can inhibit, whereas some could actually be positive. A good example of this is fine touch, discrimination of 2 points. I don't know if I did this guy with you guys yet. But it's taking 2 pencils, put them right together. Okay? Now, there's 2 points there. If I take those 2 points and put it on your back, whether I go with 1 point with this or 2 points over here, you can't tell the difference. Does that make sense? You can't. You could just feel pressure there, but you can't tell 2-point discrimination. But if I put these 2 things on my lip, a little bit more sensitive, I could feel the difference there. So that's what we call 2-point discrimination. Okay? Then we have convergence, where we have a bunch of neurons converging onto one. We could have divergence, so one neuron could actually diverge and go to a few different ones. We could have, this one's kind of confusing, but instead of negative feedback, it's going to slow it down. It's going to continue and say, it's a cycle that repeats and repeats and just says, keep on putting more action potentials down here. All right? This is reverberatory circuits. They continue and continue and continue. Or we could just have neural nets, which really is self-explanatory. They're all over the place. Okay? What questions do you have?